the lecture. So yeah, it's a great pleasure to have Professor Juan Maldacena from IES Princeton, and we all know his contributions, where he has made a tremendous contribution in the field of quantum gravity, quantum field theory, condensed matter, cosmology, and I hope today he will tell us something about his views of quantum gravity in the laboratory. So the floor is all yours, Juan. Thanks a lot for being here today.
Oh, okay, well, thank you for the introduction. It's a pleasure to be here. So first of all, let me say that I will welcome interruptions and during the talk and questions and discussions. I wasn't sure exactly what the audience is. So let me start with some general remarks. So when we think about quantum gravity, so we first think, well, our world is described by the Einstein theory of gravity. And by quantum gravity, usually we mean the quantization of that theory, of the Einstein theory that describes our world. And we only know how to quantize it as an effective field theory because its coupling constant is dimensionful and set by the Planck scale. And basically because the Planck scale is very tiny, quantum gravity effects are very small in more practical circumstances, even during inflation, which is the perhaps highest possible scale. If we have very high scale inflation, even then quantum gravity effects are of order 10 to the minus 5. And well, they have some effect in terms of creating gravity waves, and that might be a way to see effects of quantum gravity. But I think here the discussion during this talks is mainly about gravity effects that we can see not through cosmology, but in more direct experiments. Now, if we think about quantum spacetime in general, so if we are a theorist, then you could consider quantum gravity more generally as any theory where spacetime is dynamical and quantized. In particular, you could consider quantum gravity in dimensions, in 2 dimensions, 3 dimensions, 10 dimensions, 11 dimensions, any number of dimensions you want, as long as you are summing over geometries and you have some kind of quantum spacetime, you could still call it a theory of quantum gravity. Also, the matter content beyond gravity could be different than the standard model. We could have other kinds of matter. Also, the cosmological constant could be different. Maybe instead of an expanding universe, we could consider a static universe, a flat space, etc., negatively curved space. Now, one generic point is that black holes are one of the generic predictions of theories of gravity. And so quantum aspects of black holes is something important to study in quantum gravity, or something you could study in these various dimensions that we are discussing. That's in theory. So as a theorist, you could do this. Of course, it seems at first sight that this is not very relevant experimentally. So theorists have been studying quantum gravity theories in this general sense for many decades. And one general idea that is apparently true is the following that came out of these studies, is that in some cases you can get quantum gravity from ordinary quantum systems. So, and that's will be the main thing I will try to explain during this talk. So the idea is that some quantum mechanical systems, so certain many-body interacting systems, appear to have an alternative gravitational description. So the type of systems we are discussing are systems with n bodies. By n bodies, it could be like n qubits, for example, or n Majorana fermions, or sort of n pieces somehow. That they all have typically they have, let's say, all-to-all interactions and fairly strong interactions. And the idea is that such systems, under certain circumstances, they behave as if they have some emergent space directions, so that were not manifest in this description. Was there a question? No. Okay. So there was some emergent space direction, and if the system is at finite temperature, then there will also be some black hole in that emergent direction. So typically, you have a geometry that contains a boundary, some emergent direction, and a black hole. That's roughly this picture here. We're only drawing the space direction. If we think about the whole space-time evolution, so when we evolve the system in time, typically in the geometry, we will have a so-called diagram roughly like this. There is a time direction, and there is an extra immersion direction, which here is horizontal. And then there is a black hole horizon, and there are some singularities beyond the black hole horizon. So that's the type of geometry that we get. And there is a sense in which there is a boundary, so a region where perhaps the gravitational description ceases to be valid, or maybe there is a sense in which the gravitational potential here becomes very strong and pushes things away from the boundary. Now this goes under many names. So the name would be holography, ADS, CFT, gauge gravity duality, gauge string duality. And so all this, the names are more appropriate perhaps for various examples, but you might have heard it with these various names. And I will describe some examples, more concrete examples in a second. So the idea is to connect it to the discussion on the lab. The idea is that by artificially manufacturing these strongly interacting quantum systems, we would have a whole little universe to study somehow. We would create a system that would have this immersion time space directions and so on. And in this way, we could study quantum gravity theory experimentally in this sense. I mean, in the end, what you are doing is just studying particular many-body quantum systems. And so the gravity interpretation is some theoretical prediction, if you wish, for these systems. And more generally, you could think of this as an intrinsically interesting phase of matter. So there is some phase of matter which contains an emergent extra dimension and some kind of emergent gravity. So that's what we would like to understand.
Hello.
Yes.
Sorry, can I ask here a precision in the type of condensed matter, that example of condensed matter that you talked about? How do you define really gravity? What is gravity for? I mean, in this type of systems? Or
yeah. So by gravity, what I mean is a theory that involves a dynamical space-time that could be in any number of dimensions, could be 1 + 1, 2 + 1. In some of the examples I would discuss would be like 1 + 1 dimensions. So I think the general definition would be one where there is a certain geometry and we are summing over geometries. So it's, if you wish, a more theoretical, what I'm giving you is a very theory-oriented definition, which involves the mechanism of calculation, or the mechanism by which the theory is defined.
But the ordinary system, or in the, I mean, at least when we don't consider the real gravity, they are yes. in yes. flat space-time.
Yes. So yeah, this is the gravity I will be discussing throughout my discussion here will not be the 4-dimensional gravity that we were talking about here, right? So we have 4-dimensional gravity in our own world, and we could study that theory of gravity, which we think would describe the quantization of the Einstein theory in our world. That's not what I'm going to be discussing.
Okay, thank you.
So we have 2 steps. Well, first there will be this step where we think of theories of gravity more generally, in the sense of in various dimensions and with various matter content and so on. These are not the theories of gravity that describe our world. But some of these theories of gravity could be related to these quantum systems that we're discussing.
One quick yes. question. I don't know whether this is the right time for this question.
Yeah, please. Yeah.
Is the other, so you can emerge only one dimension, one extra dimension, right? Is it possible so far to emerge?
Yes, yes. Well, usually there is one interesting dimension, which is the one that is sort of goes away from the boundary. Mm-hmm. And then there are some examples where you emerge many, would say, less interesting dimensions, which are compact spaces, like a sphere and so on. You could also have such examples. We could perhaps discuss them later.
Okay, thank you.
But yeah, usually there is, let's say, the one very non-trivial dimension that emerges is this radial direction. So there is time. Time is usually present in the boundary theory. There is an interesting question, conceptual question, which is what the time here inside behind the black hole horizon means in the boundary theory. That's a question we don't currently understand, but so not everything is understood about these discussions. So I think if you could say that this is just an interesting phase of matter with some emergent extra dimensions and emergent gravity, and you might want to study it just because it's an interesting phase of matter. So that's one reason to consider it independently of whether you're interested really in gravity in our own world. Okay, the real 4D gravity. So I think another way you could think about this is as models of analog models. So people have previously discussed, for example, sonic analogs of black holes, sometimes called dumb holes, and they have some features that resemble Hawking radiation, but not other features like black hole entropy and so on. Now, the systems that we are discussing that I was referring to and that we'll discuss later in the talk are a better and more accurate analogy to black holes. So if you wish to 4D black holes, but they have more features of black holes, like they have an entropy, they have Hawking radiation, they have all these features. Now the question let me just frame this question a little more. So there are, in this connection between quantum systems and gravity, there are some wild hypotheses. So there is a wild conjecture, which is that any quantum system has an alternative description in terms of a theory of gravity in some universe or with some kind of boundary. The problem is that we don't understand quantum gravity so generally, so this statement, whether even it's true, it's not very useful. There are some statements which are very concrete. So we have very specific quantum systems typically with lots of symmetry, large number of qubits, and very strong interactions that have a very concrete Einstein-like gravity description in higher dimensions. And the problem with this is that, well, this theoretically is very crisp and very clear what the statement is, but these systems seem to be very hard to realize in the lab. So I'll mention them at the end, but will not discuss them very explicitly. And then there is some intermediate situation where there are systems that are simple enough to be realizable and interact strongly enough to capture some important important properties of a theory of gravity, but the gravitational description is not as crisp and as clear as in these more concrete examples. So that's roughly what happens. So maybe this is another way to express the same thing, is that, well, there are the experiments we can do, which typically, so there are two axes here I've drawn. I mean, there are many more axes, but there is the number of particles or quantum degrees of freedom in your experiment and the coupling constant. And so we could imagine experiments with small number of degrees of freedom and coupling constants, which are large. And then there is the in theory land, so things that we can analyze theoretically. So we can take n to infinity, at least in theory, and analyze systems which have strong coupling and large hands and very specific systems. And some of them will give rise to Einstein gravity. And okay, so, but these are very hard to simulate. So the idea is to find some system here, some compromise in the middle, where you have some features of these systems and something that you could perhaps do in experiments, maybe not today, but in some near future. And one model that I will discuss in detail is a certain large N SYK model, which has some features of gravity, not all the features, but many interesting features. And that might be a model that is a little closer to what you could do experimentally. So I will discuss mainly this model. Now, before I start discussing these models, I would also like to mention that this connection to quantum systems is something that was originally motivated by black hole. And more precisely, was motivated by Hawking radiation and black hole thermodynamics. And perhaps one way to state it in the study of quantum black holes is as a certain hypothesis that we have called central dogma certain hypothesis. It's a hypothesis on how quantum information works with black holes, and it's the idea that a black hole, as seen from the outside, can be described as a quantum system with s qubits or s degrees of freedom, where s is the area over 4G Newton. So that's a general idea, and these particular dualities with quantum systems and so on are more specific forms of this idea. And also part of the conjecture is that this evolves according to unitary evolution. So this is an idea that presumably holds for ordinary black holes in 4 dimensions and holds in any theory of gravity. But it's an idea that has led to this relationship between quantum systems and gravity, which are a little more concrete for very specific theories of gravity. So a more, by better I just mean here, more concrete version. So more concrete version is one where the black hole is in some specific space-time. So simple examples involve negatively curved spacetimes. And then those could be the same as certain quantum systems at finite temperature. So when you have a black hole, your system is at finite temperature. And so the idea is that building up this space-time around the black hole, you can isolate somehow this black hole from the rest of the universe, from the rest of our universe, if you wish. So you, by having these quantum systems isolated from the rest of our universe, you create they create a space-time and the black hole in it. So this type of, yeah. Was there a question? No.
I think just missed connection from someone.
Okay. So these black holes in this universe are a bit like a black hole in a box. So the universe, there is a sense in which this universe have a boundary. So like in this example of hyperbolic space, even though it's infinite, there is a sense in which they have a boundary and signals reflect from this boundary. And so it's a bit like having a black hole in a box. It's a very natural gravitational box. So the simplest kind of box you could consider is a system with most symmetries, as many symmetries as you want. That would be nice. But one particular symmetry that is useful and present in most of the examples people discuss is a scaling symmetry. And that symmetry, that scaling symmetry is somewhat related to the motion in the radial direction. So it's related to the emergence of the radial direction in some way. Now, in a finite dimensional Hilbert space, we cannot have a continuous scaling symmetry, but we can have an approximate one. And so this is important for what I'm going to say later. And these approximately critical systems have some common universal features. Again, they form a kind of phase of matter with some common universal features that govern many of its properties. So I will start discussing 2 examples. One will be the quantum system, and the other is a certain type of black holes. The 2 examples are not identical to each other, but they share some common features. So let me start from the quantum mechanical example. So we have a concrete quantum system. So it's a system of n Majorana fermions. So we have fermionic operators that obey these anti-commutation relations. And Majorana fermions are roughly like the square root of a qubit. So 2 Majorana fermions are essentially 1 qubit. And then we have a Hamiltonian, which contains interactions between 4 fermions, or we could say 4 fermions at a time, in the sense that we have a sum of terms in the Hamiltonian, each of which contains 4 fermions. So each of the terms contains 4 fermions. I mean, the simplest model you might have thought would be one that would contain 2 fermions, but that model is kind of too simple. It's integrable. So the simplest interesting model is this one that contains 4 fermions. Each term will have some coupling constants, denoted here by J. So some coupling constant with dimensions of energy. And the idea is that we pick these coupling constants at random from a random distribution, which is the same for all the couplings. So we have a large number of couplings because we have n fermions. There are 4 indices here, so we have further n to the 4th couplings. And so these are some couplings with dimensions of energy. So if we are at very short times, these couplings are not important, but as we go to longer times or lower temperatures, then the coupling will effectively become large. So there is a strong coupling region, which is considering times J. J is the energy scale of these couplings, which are large. So if they are larger than 1, then we're in the strongly coupled region. And if they are smaller than n, then the quantum gravitational effects will be relatively small. If actually it's actually interesting, and later I will discuss how it is possible to go to values here which are of order n, and then you are studying some strongly coupled gravity effects. So that would be
One. Can I ask a quick question here? So this why is this by n cube dividing by? Is there a particular reason for?
Yes. So it's so that choice there was made so that the effective coupling at the temperature beta is of order beta j, right? So the corrections to the free theory will be in powers of beta j with no factors of n.
Okay.
It's just for that purpose. There is no conceptual significance to this. If we hadn't put this here, there will be factors of n here.
Okay. Thank you.
Yeah.
A quick question.
Yes.
Is there a circuit equivalent of this model?
Is there a what?
Circuit equivalent, quantum circuit, instead of writing a Hamiltonian. I mean,
yes, you could imagine that. So I think if you press me more on that, I would let's say bosonize all these fermions, and then you would write them in terms of sigma matrices and qubits, and then you could imagine. So each term in the Hamiltonian is a particular gate, and you could apply all these gates, and you will have a circuit version. Of course, it would be a situation where you are discretizing time, right? So.
Yeah, that's it. Okay.
Yeah. I mean, people have considered. You can consider other things. So sometimes people discuss Brownian circuits. So these are situations where you have quantum circuits where the gates are random, right? You choose them at random, and they have some properties that are, well, they are not identical to this model. But some properties are also in common, and they're easy to analyze if the couplings are all random.
I guess the question, I mean, part of the scale invariance that you were talking about earlier, how would that, I mean, if you lose energy conservation, I guess. So how does this? There's no.
Then you will not have that scale invariance. So the scale invariance, I think, well, at least that feature of the scale invariance and the two-dimensional, some connection to the gravity theory is most clear if you have energy conservation.
Okay.
Now, it could be that there are also some other versions of gravity that are related to the models, the circuit models you have in mind. There will be, I don't know exactly what it is, and it would be some weirder theory of gravity than what we're discussing here.
And Juan, maybe another quick question. So the rationale for choosing Majorana fermions here rather than just 4 qubits, the 4 qubits is a more complicated theory. Is that right?
Yeah, that's a bit more complicated. Yes, and so people have also analyzed systems with bosonic variables, more like qubits or sometimes bosonic fields. They tend to have slightly more complicated phases with spin glass phases and so on, but they have also been analyzed. So here, these are the simplest ones.
Simplest, okay. Thank you.
Okay, so that was the quantum system. So now I'm going to discuss something else, which is a gravitational system. So let's imagine we have, for example, a 4-dimensional black hole that is charged. So a charged black hole, let's say, carries electric or magnetic charge. And then, so such black holes have to have a mass which should be bigger than the charge in order, so all the regular solutions without singularities have masses bigger than the charge. And when the mass becomes close to the charge, then they develop a long throat. There is a kind of critical phenomenon where the black hole develops a very long region between the exterior and the black hole horizon. So the distance between the horizon and the exterior grows. And there is a region here that looks a bit like an act. So it's a region with constant, almost constant size for the S2. And then the two-sphere, and then the time and radial direction form a simple negatively curved space, which is the Lorentzian analog of hyperbolic space, which is sometimes called anti-de Sitter, two-dimensional anti-de Sitter space. So it's a space which has a large gravitational potential pulling you towards the interior. Now, the idea is that there is some relationship between this SYK model and this ADS2 space-time gravitational dynamics. They have some features in common, and then also some features which are different. So let me just say a few words about two-dimensional gravity. So gravity in 2 dimensions is very simple because there are no propagating modes. But despite this fact, there is actually one gravitational degree of freedom which lives at the boundary of your space. So in some sense, you don't have a graviton that lives in 1+1 dimension, but you have a kind of gravity degree of freedom that lives in 0+1 dimensions. And this degree of freedom is essentially connected with energy conservation, both with energy conservation and then some other features related to the time translation symmetry. And so gravity in 2 dimensions is very simple in that sense, yet it still contains black holes. So one interesting aspect about black holes is that they don't need a graviton to exist. So you could even have black holes in theory with no gravitons. So such as these 2 or 3 dimensional theories. So in 3 dimensions also, you don't have a graviton. In fact, this is related to the fact that there are no spherically symmetric gravity waves, but there are spherically symmetric black holes. So that's another way to say this. So this simple two-dimensional gravity theory has this gravity mode, and then it could have matter fields that live in the bulk of the spacetime. And the simple boundary gravity mode is common between SYK and gravity. The matter fields are rather different. So so for example, in the example that we discussed in 4 dimensions of the 4-dimensional black hole, we would have this boundary gravity mode is something that is a mode that lives in this connecting region between flat space and the throat. And as you excite it, you make the throat longer or shorter. That's roughly what its role is. And then you have lots of fields that could live in this region. So you could have excitations with angular momentum on the sphere and all that. So those are some details of this 4-dimensional setup that you will not have in the SYK model. So those are some of the differences. Okay, let me, this is another picture of the 2-dimensional gravity in the case that we have a black hole. So we have a very simple negatively curved spacetime, which is this ADS2. ADS2 has a Penrose diagram, which is a strip like this, infinitely long in the future. There is a vertical direction, which is time, a horizontal direction, which is space. And there is a gravitational redshift factor, which pushes particles to the center of the spacetime. So it becomes very large near the boundary and order 1 here in the middle. So if you have a particle moving in the spacetime, it will oscillate around the center. So this is just describes one portion of this oscillation. The boundary in this region, so the region that would connect to flat space. So this would describe an infinite throat. If we have a finite throat, there is a red line, and we are cutting off the exterior of this red line, and we are only keeping the interior. And so the position of the red line tells us how long the throat is. So the distance between the horizon and the boundary. And so that's now here I've only discussed the geometry purely outside the horizon. So I cut out the part that is irrelevant, that is behind the horizon. And here there are various things we could do. We could make observations, so we could excite something here at the boundary. Send the particle and see what we see some moment later. The particle might fall behind the horizon. It can do various things. But we could define correlation functions of operators at various times. So at time t1, time t2, so there is a time direction here along the boundary. that is identified with the time in the quantum system. And so if we make some observations on the qubits of the quantum system, that might be related to sending in some particles in the bulk here. I mean, we can also calculate the free energy and entropy of this black hole and compare it with the entropy or free energy of the quantum system. Now, I've said that these two systems have the same symmetries. They have this emergent scaling symmetry, and that's very strict in the sense that it can determine completely the functional form of this two-point function. So time translation invariance implies that it's a difference of time, but the scaling implies this very specific function, which is a hyperbolic sinh of time difference. And there is some associated scaling dimension. So up to these numbers that, well, in principle, you don't know, but you can calculate in SYK, you have this two-point function completely fixed. In addition, the entropy or thermodynamics of the system has the feature that at low temperatures, it goes low, but not super low. They go like a constant plus something linear in T, okay? And so constant would be the scale invariant answer, which would be independent of any scale. And this is a small correction to scaling, which can be computed. And what is characteristic is that it is linear in the time. So these two features are common to SYK and the black hole situation. So also for near extremal black holes, we have this feature for the entropy.
And does the constant also change with the scale? This
constant is independent of, this is just a number that needs to be calculated in each case. And it is different between the black hole and SYK. But yeah.
And in this thing, the psi i's are the psi i's are the bulk.
Yeah, the psi i's are for example, the fermions of SYK. The SYK model.
Okay.
The chi's, you could interpret them as fields that live in the bulk of space-time. They could be bosons or fermions. So this formula is actually the same for bosons or fermions.
I see.
So they could be, let's say, the value of a scalar field near the end of the throat region.
Okay.
They could be the value of the electromagnetic field. They could be a fermion. That lives in the bulk. So that's what it is.
Okay, thank you.
Now, so we have some, the matter, so there are some features that are completely determined by the conformal answer, and then there are some corrections to the conformal answer that are controlled by a single mode, and you can identify this mode in the SYK or in the gravity theory, and it's a kind of collective mode. It's somewhat similar to the phase of a superconductor. I mean, we could say that in a sense, we have a kind of time superfluid or a space-time superfluid. And so it's a collective mode that governs some corrections to all these formulas. And in the gravity picture, it corresponds to the position of the red boundary we were discussing here. So this boundary can move, and the motion of that boundary is some particular degree of freedom, which is easy to identify in the gravity picture, but can also be identified in the quantum system. And in SYK, we can derive its dynamics from a certain large N analysis, which is somewhat similar to the analysis that people use for the BCS theory of superconductivity, if you're familiar with that. But so for some analysis roughly similar, you can derive the dynamics of this particular mode. And this mode is present in both cases, and anything related to it will agree between the two sides. So in this model, I tried to make a schematic picture. So we have on one hand the SYK model, on the other hand this nearly ADS2 gravity. And then we can go to low energies on the SYK model, and there is a piece which is conformal, some conformal invariant part of the model, and then some piece that has to do with certain collective excitations, let me call it some time reparametrizations. Here in gravity, we have some quantum fields that live in ADS2, and then we have the dynamics of the boundary particle. And the idea is that these two are precisely the same, so they're precisely the same degree of freedom. These other two are rather different. They are not the same, but they have the same symmetries, but in detail they are different. And this part that is the same, there is some very explicit action that we can write down. I perhaps will not discuss it in detail. It involves the Schwarzian derivative of some function of time. U is time here. And this describes the either you can call it the boundary graviton. And so there's a pattern of symmetry breaking that governs the form of this action. I won't discuss it in detail, perhaps I want to mention. But this action governs a bunch of things. So first, it explains why the low energy temperature is linear in T. Then it governs some effects of gravitational back reaction, that if you send in a particle, then you change the temperature of the black hole and so on. And then there are some more detailed things that have to do with the particular form of quantum chaos that this model displays. It fixes the sort of Lyapunov exponent or a certain property of that quantum chaos. And then there are some issues related to wormholes that I will discuss later. But all of those I agree between the two. So let me just show you how, at least from the gravity point of view, things work. So if you look at the trajectory of this boundary particle, this is without any perturbation. We have a horizon. And if you send in some particle here from the boundary, it turns out that the trajectory of the boundary particle will move. That's this gravitational degree of freedom, and will hit and will move it. So that means when you tackle that was here was visible from the boundary before you did this perturbation and not after. Okay, so now I'd like to give a picture for what this whole wormhole corresponds to. So the idea is that we have these two boundaries. So let me first describe the gravity picture. So in gravity, there is a natural solution, which is the analytic continuation of the black hole solution, which contains really essentially two black hole exteriors that are united, they're connected through the interior. We can call this a wormhole, a Schwarzschild wormhole. This is present in the original Schwarzschild solution, though it was recognized many years later. And the idea is that this spacetime is related to a particular entangled state between the quantum systems. So we have two SYK models, and if they are in a particular entangled state, which is called the thermofield double state, given by this formula, then the geometry would be connected in the bulk. From the boundary point of view, all you have is just these entangled states. Yeah, I'm not sure how we're doing with time. Maybe
you have time, half an hour.
I have time, yeah. So maybe I'll discuss a little more how to make this state and whether it is practical or not to make this state, because it's well, first of all, from the gravity point of view, it's a weird state, but that has interesting properties. So I'll try to describe what those interesting properties are. So there is the question of whether you can make actually this state, and can one check somehow that it is geometrically connected? We can explore some symmetries of these states and perhaps other interesting things we can do with it. So the first question is whether we can actually make this state. And the idea is that we can take two decoupled quantum systems and add a small interaction, which in this case, so these are two identical systems, but decoupled from each other. And then you add a small interaction, which involves all the fermions. Here, when I say identical systems, I also imagine that the couplings are also identical. They have exactly the same couplings. And in this case, the ground state of this model would be this, would be close to the thermofield double. So that's in SYK. In gravity, we could imagine taking two extremal black holes that are relatively close to each other so that they interact a bit, exchanging some fields. And the idea is that they will create a wormhole. And indeed, we have found wormhole solutions which are like this. So the gravity picture of this ground state is that the boundary trajectories are now go straight up in the Penrose diagram. And you can send the signal from the left system to the right system through this wormhole. And the gravity picture is, well, this is similar to this picture where we have some wormholes in 4 dimensions, and they are connected through. Sorry, we have 2 black holes in 4 dimensions, and they're connected. Well, not holes. So we have two throats of things that will look like they are similar to the near extreme of black holes, but instead of having a horizon, they're actually connected. The 2 throats are connected, and this region of the space-time, which is the ADS2 region, is just the portion that connects the 2 throats. Now, this particular ground state has
one second. So maybe this being a bit nitpicky here. So in the previous picture, if I ask that, so when these degrees of freedom that you have are around the neck, the end of the neck, right? When you bring them close together, so they will not all interact, right? They will, I mean, those which are only like next to each other will interact, right? How general is your entangled state? Is it kind of?
Yeah. So are we discussing the gravity picture now, or?
No. So from the gravity picture, I'm taking the fact that how close those the boundary systems in the neck are, like they will be next to each other in the middle of the 2.
Yeah. So the distance here is this distance in the ambient space, right? And the idea is that due to, let's say, quantum effects or van der Waals-like forces, there is some interaction between the 2 black holes. The idea is that each black hole could be viewed as described by some quantum degrees of freedom, which are not very manifest in the gravity description, right?
Right.
And that this fact that their proximity induces an interaction, which is similar to the interaction we have between these SYK models.
Right. Okay.
And they're actually, so if you have it set up like this, you can actually find a solution.
Wormhole development. Okay.
Yeah, there's a traversable wormhole. I mean, it doesn't violate causality, so because this length is actually longer than the distance between the 2. And the solution involves some quantum effects and so on, so it's somewhat slightly complicated, but there is a solution like this.
Okay.
And here, when we draw this diagram, we are drawing only this portion of the solution. So portion here that connects the 2. So what is beyond the red line is connected to the 4-dimensional space here. Well, you don't need to understand all these details. So the important point is that these 2 sort of interacting systems have some features in common or are related to to a situation where you have this ADS2 space-time and with some interaction between the 2 boundaries. So the 2 boundaries have some direct interaction between the 2 sides that in this diagram are related to the fact that they're close to each other. So it's not surprising that you can send a signal through the wormhole because there is already some interaction between the 2 sides. What is interesting, the thing that is interesting is how this signal goes. It somehow goes through the wormhole rather than going through this naively through these interactions. Ultimately goes through these interactions. But,
Juan, if I may ask, in this case, would we expect some non-local then interactions, either in the gravity side?
No, there are no non-local interactions in any of the 2 sides. Well, let me see. If you only had the portion if you only looked at this ADS2 space-time, an interaction between this point and that point at the same time looks non-local, okay? But that only looks non-local because you're not taking into account what is outside this region. So here, let's look at this diagram. So if you only look at this portion of the diagram, an interaction between a point here and a point here looks non-local, right? Because it has to go through some distance through this wormhole. But these 2 points are relatively close in the ambient space. So there could be effectively a direct interaction. I'm saying that the length of this wormhole is much longer than the distance between these 2. So from the point of view of this wormhole, this looks like an instantaneous interaction. Is that clear?
Yeah, thanks.
Thanks,
yeah, okay.
Yeah, a lot of what I'm discussing is some kind of translation between something you see in the quantum system and what you see in gravity. And yeah, so if you just only look at the quantum system, so let me discuss a few features about this as a quantum system. So when you introduce that interaction we discussed, you get the gapped ground state, but it's not any gapped ground state. It's one where all the excitations organize into representations of SL2. So there is actually a predicted spectrum of excitations where with a spacing that has to do with, that is governed by the approximate conformal symmetry. And so, and that's related, so that those, the discreteness of the spectrum and so on is like the quantization of this oscillation of these particles, that it's like a harmonic oscillator with a series of levels which are governed by the dimensions. Anyway, so all I'm saying here is that it is some interesting state, even from the point of view of quantum physics. So these symmetries are present for the thermal field double, and they are similar to the symmetries that were governing the correlators of the thermal theory, and they're symmetries of this wormhole space-time. Now, you could wonder whether you can efficiently find this ground state. Well, maybe it's very difficult to make. But the idea is that you could couple these two models and start them out in some unentangled state, and then couple the system to a cold bath. So we have the system with interactions. Yeah.
Juan, can I make you a question? Yeah, it's simple because as far as I understand, when you have the emergent or the connection between the parametrization mode in the SYK comes after something like aberration of the over the Gaussian distributions of couplings, and when you build up this thermal field double, I understand this is built up from some concrete realization of the distributions.
Yes.
Okay, is there any issue with that, or I mean?
Yes. So the idea is that there is no issue as long as you, when you have these two SYKs, you have the same couplings between the two SYKs. So something you are not allowed to do. Well, I mean, you are allowed to do, but you would not get this state. Is that to have some couplings here and different couplings here. So that we don't want that. We want some couplings here and identical couplings here. So that's something that would be difficult to realize experimentally. Now, they don't have to be exactly the same. You could tolerate a small variation. They have to be somewhat correlated, the two couplings, sufficiently correlated. So we wrote some papers for, in this paper of with Xiao and Chi, we had couple. Well, theoretically, of course, we consider couplings which were not exactly identically correlated, and depending on the correlations, at some point you will lose the wormhole, but as long as you have some correlations, you will get the wormhole.
Okay, thanks.
The wormhole-like state becomes more fragile as the couplings get decorrelated. So it's it's a somewhat fragile state, not completely fragile.
So Juan, in this case, of course, if this is happening in nature, so even this randomness can only come from some other field, right? So a correlating random. So do you have an idea what? So it's like another.
Yeah. Well, the idea is there is no claim that the SYK model describes nature. Okay.
Okay.
So the claim is that if you were to manufacture an SYK model, so you produce some Majorana fermions in the lab, and then you engineer them so as to have these couplings, you would have to put in these couplings by hand, by bringing these Majorana fermions close together and somehow introducing these couplings. So in principle, I'm imagining that they would be under the control of the experimentalist.
Okay. Thank you.
Yeah. So it turns out that you can get this state in sufficiently relatively quickly. Now another thing you can do is the following. So imagine now we go back to the coupled system where you have two. Let's say we first could start with the entangled system. With the coupled system, we find this entangled state, and then we turn off the coupling, right? So we could do that. So we start with the coupling system. The red line, the green lines represent the coupling, and at t equal to 0, we decouple them. Then at positive times, we get the geometry which looks like the Schwarzschild geometry, and in quantum mechanics, we just have two decoupled systems in an entangled state. In that case, if we send a signal from one of them, we will not be able to detect it from the other side. Okay, that's reasonable because they are just entangled states. But if you put some interaction at t equal to 0, at time equal to 0, you put some interaction, you give a little kick to these boundary particles, a little attractive force, and then you can see a little more of your space-time. It's like you delay the formation. It's the opposite than making the black hole grow, you make it a little smaller. And then in that case, you can receive this signal. And you can view this as here we imagine applying an operator. We could apply a measurement here and then transfer the information to the other side and do a suitable operation that will have the same effect. And so this white signal then can get to the other side. And of course, we are introducing an interaction, so there is no mystery that this signal gets to the other side. What's interesting is how it gets to the other side. It's a kind of form of teleportation. So you introduce a signal, and the natural time evolution mixes the signal with the original entangled state, and then you make a simple measurement, and you do a simple operation here, and then the natural evolution somehow decodes. It's similar to the decoding transformation you do when you do teleportation that allows you to extract the signal. So it's a particular kind of teleportation where it's a special kind of teleportation, and the qubit somehow goes through the wormhole. And the curious thing is that in the gravity picture, this particle feels nothing as it's being teleported between the two sides. So if this was a complex object, then it would not be disrupted as it gets teleported. Most of what I said, this relies on the large N expansion, but experiment, of course, will involve finite values of N. And so one needs to understand the 1/n corrections. And one interesting aspect is that some of these 1/n corrections are these quantum gravity corrections. And in fact, they have been understood. So you have to understand the quantum mechanics of this boundary mode, and it's similar to the quantum mechanics of a particle moving in ADS2, and they have already been computed. So in these various papers, so it's an exactly solvable model. At least the boundary particle is an exactly solvable model. So you can get all these quantum gravity corrections. Now you can also ask the question of what is the simplest quantum system that displays this behavior? Like how many couplings do we need? And so if we have SYK with n fermions, we have further n to the 4th couplings. But it seems that to have this behavior, you don't need to have so many couplings. I mean, experimentally, it might be difficult to govern, to create all these couplings. And it's good that we only need a further n couplings with some constant, which is not too big, let's say 4. So this was found in this paper. And so more generally, you want you could imagine the various qubits as living in a kind of graph. The graph represents the connections or interactions that you have between the different qubits. And you need a fairly connected graph. So like a flat space lattice could be a kind of graph. So if you put all the qubits on a lattice and they all have nearest neighbor interactions, that's not good for creating these complex states. So you need something that's called an expander graph. So you need some interactions between sort of distant places. And in particular, you need that information spreads relatively quickly through the system. So if you are in a lattice and you change one qubit, that qubit will take some time to interact with the next qubit and so on, and takes a time which grows linearly, or let's say some power of n, where n is the total number of qubits. So here we want a situation where there are enough interactions that the information spreads through a time of order n, logarithm of n, as opposed to powers of n. And I know of one experimental paper that tries to, and there might be many others, sorry for if you're an experimentalist and I haven't included your paper, where they try to, in this paper, they create some systems with atoms in optical cavities that tries to create the so-called scrambling system. So fast scrambling system is a system where this information propagates in a time of order logarithm of n. Now I guess I wanted to mention, just for completeness, a few features of the more complicated system. So the SYK was supposed to be the simple system, But the connection to gravity was clear, but somewhat slightly complicated. So here we are going to discuss some more complicated systems that are supposed to give a theory governed actually by Einstein's equations. So Einstein's equations in certain number of dimensions. These are not easy to simulate or to create in the lab, but I just mention roughly what the spirit of those is. So a quantum system is a collection of harmonic oscillators, both Majorana fermions and bosonic oscillators, which has cubic and quartic interactions, and it has a completely explicit Hamiltonian. And I won't write down the Hamiltonian, but the Hamiltonian is governed by its symmetries. It has a bunch of symmetries, like there is a certain UN symmetry, and there are many so-called supersymmetries which relate bosons and fermions. In particular, there's also an SO9 symmetry that relates various oscillators. And the gravity system is a particular 10-dimensional spacetime, so it contains time, a radial direction, and an 8-dimensional sphere. And it is a solution which describes a charged black hole in 10-dimensional supergravity, in a very specific 10-dimensional supergravity theory. So that's an example which is completely explicit, and where you can compare the answers between the two sides. In particular, there was a paper, I forgot to put the citation, where they did a numerical analysis of that model, and they showed that it matches the entropy of these black holes. So let me mention some conclusions. So part of the conclusions are that certain strongly interacting quantum mechanical systems have common features with gravity, and the simplest examples involve these models with almost critical behavior at low energies. And the common feature with gravity involves a particular sort of time superfluid mode, which can be analyzed in detail and quantized. And there is interesting behavior when we couple two models. There is an entangled state that you can get that has features in common to gravitational wormholes. And there are many questions we would like to understand, like how spacetime appears and how we explore their properties. And for finite n, these models display, for finite n, the analysis implies that we need to quantize gravity. So by studying the finite n models, you are studying quantum gravity directly. Now, I would like to say why it is interesting to study this experimentally. Of course, you could say, okay, well, you confirm theoretical discussions, but that's not the most interesting part. The interesting part is that you could explore quantum gravity in a regime where it's not close to classical, and perhaps in regimes where we cannot analyze it explicitly through theoretical methods. In particular, we would like to understand the emergence of spacetime from quantum mechanics. We think that this happens in some examples, but we would like to understand it better. And perhaps by experimentally thinking about this, we will find new systems that display this phenomenon. So this phenomenon, theories have found it theoretically for some systems, but we are limited by the theoretical tools we have. So like we have supersymmetry, okay, then we find it with supersymmetry. We have some large n equations that were useful for SYK, and then we can find that SYK model. But maybe there are other systems that display this behavior. And even recognizing the behavior when it happens, it's somewhat subtle. So that's part of it's a subtle phase of matter. And we would like to understand how generic the emergence of a spacetime is. So are arbitrarily strongly interacting systems display this behavior, or do we need to have some other special properties? And I think that experimentally trying to construct these systems could answer some of these questions. So I think that's the more interesting reason to do this. There are other questions, like, for example, could we have a quantum system that would describe a 4-dimensional spacetime with, let's say, only 4 large dimensions and with our matter content? That would be like simulating our gravity. Yeah, this is a question you could ask. Currently, I'm asking it because we don't have a theoretical way of actually doing this. We have some examples that have, for example, 4 infinite dimensions, but 7 very large dimensions. But we don't have examples having only 4 very large dimensions and the rest all small, or maybe no other dimensions, and in particular also not with our matter content. But anyway, here I will finish with some references. So these are some references mostly on the SYK discussions. There is some paper. The last paper is a paper which is titled "Quantum Gravity in the Lab" and discusses some more specific proposals for realizing this wormhole teleportation and several questions related to that, trying to identify the simplest systems, even perhaps simpler, well, trying to identify how that teleportation works, and perhaps with the goal of finding the simplest possible system that displays that kind of teleportation. Okay, that's all. Thank you.
So thank you very much, Juan, for this very exciting and very mind-provoking talk. And so we already have a few questions from the audience, but this is a good time to ask Juan your questions. Please just raise yourself and ask. Yeah, Jonathan, please.
Oh, thanks for a great talk, Juan. So I hope people can hear me. It's a bit noisy. Can you comment a bit on like the when you're in like SYK and some of the other models, when you have an ensemble, can you comment a bit on like what are the features that you don't expect to be transferred, or you don't expect?
Yes. Yeah. So all the features I discussed today, we expect that they are true for specific members or for specific couplings. So they don't. So all the features I discussed today, they don't depend on doing the average over all possible couplings. So experimentally, you wouldn't need to have some couplings and do some experiment, and then have some other couplings and repeat the experiment. It would be enough to just simulate the system with one choice of couplings, and they will have all the features that we discussed today. There are other questions for which where you would get differences between the system with where you average over the couplings versus the one where you don't average over the coupling. But these are questions we haven't discussed today.
Are there specific things when you average that would lead you to get kind of results that you would not expect in a quantum gravity system?
Yes, that is true. So, well, the average over couplings is something you can do theoretically. I mean, from the point of view of practical experiments, you would have some values of couplings, and that would be the more relevant situation. So if you average over couplings, then you would not necessarily have a unitary results, in the sense that if you calculate for example, if you have a density matrix and you average the density matrix, then it's squared. You will not obey the properties that you expect. So if you have let's say a pure state, so suppose you have a pure state, then the density matrix, its square should be equal to the original density matrix, right? But if you first average over an ensemble of couplings, then that pure state might change, because it's like the ground state for different values of the coupling, and you will not have a pure density matrix. So that there are some questions like this which are different if you average versus if you don't average. But I would say that this issue for an experimentalist, this issue of averaging over couplings is irrelevant, in the sense that it's a problem for theorists, that theorists will have to predict the behavior of a system with specific couplings. So the averaging over couplings is a theoretical tool, does not appear to be fundamental.
Thanks.
Hi, I would like to ask you a question related to wormholes and entanglement. Yes. Is like the possibility of working on like some experiment which relates this to the factorization problem on ADS, FT, and yeah, something.
Yeah, so I think if you if you do the experiment, the systems will factorize, because the quantum systems are, if they are decoupled, they will factorize properly. I think, yeah, I'm not sure what experiment you could do. I mean, you could, well, there are certain observables that people have discussed that receive a contribution from wormholes, such as long time correlators at very long times and so on. And in principle, you could imagine looking at these observables and seeing and measuring them and seeing what you get. So far, people have done these calculations using classical computers. So they looked at this observable using computer simulations. Presumably, you could do them using quantum computers and perhaps discover some new features that they have that are hard to theoretically calculate. Features that reflect the fact that the energy levels of a black hole are discrete and things like that. I think that's what you're referring to. Well, I don't have a concrete proposal for something that you could do.
Okay, thank you.
Yeah. I think it's a good question.
Okay.
Yeah, Music, please go
Yeah.
ahead.
Thank you very much for your talk. Just out of my ignorance, so you mentioned the entanglement many times. Is there any particular role entanglement plays in your work? Because, for instance, in condensed matter physics, sometimes entanglement was seen as a sign of phase transition or something like that. So, is there anything? Yeah.
Yeah. So I think it plays a role similar to the role played in condensed matter, in the sense that this state that we're discussing that has this gravity description has particular patterns of entanglement that need to be true in order to have the gravity correspondence. Entanglement of subsystems have to have certain properties. So I think it's, yeah, I would say it's similar to the condensed matter discussion. So, for example, if you are talking about this wormhole, then it has to have a particular pattern of entanglement. And yeah, and that's a feature. That's a necessary feature for the wormhole. Not sufficient, but necessary.
Has it been extensively studied? I mean, that kind of things.
Yes. It's been studied a lot, and especially in higher dimensions. So I've discussed systems which are all at the point, all interactions that are local. But we could have systems like where the quantum system is in higher dimensions, let's say 1 + 1 dimensions, etc. And then you can look at entanglement of various subregions, as people do in condensed matter, and they are related to various properties of the bulk space. So the main reason is that there is a formula in gravity for the entanglement entropy that says that the entropy is a certain minimal area in your space-time. So it relates to a geometric feature of the space-time. In 2 dimensions, the areas are just points, and so that formula is relatively simple, but it does play some role in the teleportation discussion. But in higher dimensions, it plays a role in fixing more aspects of the gravitational solution of the geometry.
Okay, thank you very much.
Yeah.
Thank you.
So yeah, Arijit, could you please?
Thanks for the very interesting talk. I have 2 questions. One is, I mean, this SYK model is this infinite range model. Is there a way one can go away from the infinite range sort of limitation? And if one looks at longer range model instead of infinite range, somehow, is it possible to write a model which still survives at least qualitative features?
Yes.
And the second question is, okay, I mean, okay, yeah, why don't you answer?
Yeah, so I think the basic idea is that the effective, so you want to have enough qubits that are strongly interacting, and the number you have that are strongly interacting with all-to-all interaction determines how classical your bulk is. So if you want your Newton constant in units of the radius of, let's say, the space and so on to be small, then you need to have all these all-to-all interactions. So I mean, you could consider a system which is 1 + 1 dimensional, and the interactions are, let's say, short range and relatively medium range up to, they involve 10, let's say, nearest neighbors, but not 1. Then your Newton constant in units will be of order 1/10, right? And if it involves 100, it will be 1/100, and so on. And in that case, the bulk would be not 2-dimensional, but perhaps 3-dimensional. And if you have an infinite, let's say, 1D system.
I see.
And so you have,
I see. So my second question was, I mean, you have this thermal feed double state, which is sort of a signature of the wormhole in some sense. Right. So, I mean, these are, if I understood it correctly, these are two highly entangled sort of states, which are have a certain pattern of entanglement between them.
Yes.
So say in some sense, these highly entangled states are thermal states in themselves.
Yes, exactly.
Yeah. So now in a physical setting, this state is actually quite unstable if you perturb the system weakly, because you would couple them. Say, suppose you create two thermal regions of this specific model,
yes.
And you perturb it, and they are entangled very weak. They're entangled just enough to have the wormhole, but not too much.
Yes.
Because but if you perturb it weakly, I would have thought you would destroy this very delicate pattern of entanglement between them. Or is there a reason why it should be protected? Is there
you're absolutely correct that so you should think of so somehow this particular thermal field double describes the state at t = 0, where there is, let's say, some distance between these two boundary particles. So even just evolving it to the future without the coupling changes the pattern of entanglement, changes the form of the state, and leads to a further distance between the two boundary particles. Okay. And if you do some random perturbation to one of them, it will even increase the distance more. So that's related to this instability that you are discussing. So that it's related somehow, it's a bit connected to the instability in negatively curved space, that two particles which are initially parallel, they start moving away from each other. Anything you do, you will move it even further away. It is indeed an unstable state. You can make it stable by, I mean, you can make it a ground state by doing this thing that we discussed at this point in the talk, of putting a small interaction. So there's a small interaction you can add that makes it a ground state, separated from a gap from other things. So it gives it some stability.
But the ground state will have I guess the ground state having volume law entanglement, I guess, I mean, these thermal states will have volume law, at least in sub-region.
Well, remember that we are discussing all-to-all interactions. So
I see.
Yeah. So yeah. Now, if we had a system that has some extra dimensions, right? I haven't discussed systems with extra dimensions, but if you have systems not in 0+1, but in 1+1, 2+1, etc., they would be related to gravity theories in those dimensions. And so, for example, this diagram of the wormhole that we were discussing here, there would be an extra dimension that comes perpendicular to the screen, right? And so that direction perpendicular, so the wormhole would be translation invariant, for example, in the direction perpendicular to the screen. And the entropy of the wormhole would be the area of this horizon, which is, well, it's proportional to the volume, to the volume of the system. So there is a volume law entanglement that comes from well, it's just the same as the thermal entanglement, but here it's entanglement between one copy and the other copy.
Okay, thank you.
Yeah.
So Juan, I just had one question. So is it possible to construct what you have constructed, but with the say, let's say one graviton system, like one photon system is actually highly quantum.
Yeah.
Similarly, one graviton system will be extremely quantum, although you say that, oh, it's a very small number, less than perhaps, but it's highly quantum system. So is it possible to replicate what you have said just for this kind of system?
Not that I know, no. So here we are connecting sort of strongly interacting quantum systems to gravity. I mean, if you had, let's say, flat space and you have just one quantum graviton, I don't see what we can say that is in this general direction.
I see.
I mean, there are probably other things you could say, but.
Also, experimentally, it is viable. I mean, in a real life experiment, because we can only play with very small masses due to decoherence and all these problems which we face in the
yeah, it's of course.
That's why I asked this question, that if we can have a even theoretical description of one graviton system or something like one or two.
Oh, no, we do have a theoretical description of a one graviton system, right? So just the gravity as an effective field theory. I mean, we can quantize gravity, right, in our real world as an effective field theory, and we have a description of a one graviton state. I mean, it's not very different from a one photon state, but that's a theoretical description. Unfortunately, that same theoretical description predicts that, well, at least that there is no way to observe anything related to it, at least known way. So I think the only thing that I know that leads to that you could say it's related to quantum gravitons is the observation of primordial tensor modes from inflation.
But even then it is very hard, because who knows, the initial conditions could be purely classical. That's also...
Yeah, it would be hard to perhaps prove it's really quantum, but at least there is a theory that predicts them. And yeah, that's right.
Thanks. Any other question? Yeah, I could see Ben. Yeah, please.
So I'm just wondering. So let's say we have a gravitational wave that passes through, say, some material. So classically, we expect that it is towards the object. Now, if we think of it as like a quantum object in parallel with like photons, so would the object being heated up depends on its energy levels? So in other words, will we have gravitational insulators or gravitational conductors?
Yeah, I think so. I mean, there will be yeah, I guess you're imagining a material where there is, let's say, a band gap, and you have some gravity wave within this band gap, and then it will not excite, let's say, the electrons. I think that's, yeah, that would be true.
Thank you.
Then I could see Andre, please.
Yes, hello. So my question is, in that case, I saw it was really nicely explained how you said that you can see a bit more space-time due to the entanglement, and that due to the affinity 1/n expansion, you would see some quantum gravity effects. But in this limit, basically, all experiments are going into this, I mean, into this level of finite n or small n. Would it be possible to discern somehow what is specifically quantum gravity? And on the other side, in the case of string theory, for example, what would be the analog of ERDPR in that case?
So regarding your n, so there are some so there are some correlators which you can whose correction 1/n corrections you can calculate, and people, let's say, doing calculations with n equal to maybe 30 or 40 for SYK, right? Have managed to they did numerical calculations in classical computers, and they found that they found a correlator, and it matches well with the quantum corrected correlator, but not with without putting the quantum corrections. So I mentioned that people had done some corrections to gravity, and these people have computed corrections to the correlators, and they match well with the numerical simulations. the point is that the n, so yeah, the energy levels of the system are exponentially, there's an exponentially large number of levels, right? It goes like e to the n or 2 to the n over 2. And so an n of order 30 or 40 still implies lots of energy levels. So you can trust many 1/n corrections. And so you get a pretty good agreement with those quantum corrected correlators. Presumably, if you could do this in quantum simulator, you could do maybe more complicated correlators. You could study other systems, which are not SYK, other interacting systems, and see. I mean, it would be interesting to study systems which maybe whose theory we don't know. Right? Then you would discover that they are similar. Let's say they also have similar properties, for example, to SYK, even though they are not SYK.
And in the case of string theory, or for example, in the case of a decaying brain, or like tachyonic instability in the brain, would we have something similar, like entangled state of brains, of brains, for example? Yes. Or tachyon condensate entangled.
Yeah, I don't know. I mean, it's true that when the radiation that comes out of these deep brain decays is in some coherent state. I mean, it's more like in a coherent state of particles.
Yeah.
And yeah, I guess in that sense, the different particles will be entangled. I mean, it will be in a pure state.
Thank you.
I'm not sure what more you can say. I mean, we have some, in some simple models, two-dimensional models, we understand what these brain decays lead to very specific states that we can calculate that they are pure states, but yeah, I'm not sure exactly whether that's what you were asking about.
Yeah, I think Dominic has a question.
Yeah, so just a brief one. So I understand that, so when we have SYK model, we had this like 4 fermionic interaction, and I was just wondering whether it's perhaps possible to have like a larger family of these models, like relating to Sugata's comment, like about the spins instead of, with fermions. And because I've heard about like these spaces matter like fractons, where we might have some gravity emerging and this sort of stuff. So could you perhaps comment on this?
Yeah, in principle, you can have something much more complicated, and we don't know. I guess the first thing is that you have to work to analyze it, and it's not obvious you will be able to analyze it if you have, let's say, spins as opposed to fermions. Yeah, so that's a general comment. And yeah, I think we don't understand very well what the whole space of models is. So there are a few models we can analyze. There are many more models we cannot analyze. So yeah.
Okay, so it just reduces to like whether we can solve the model or not, and we are unable to kind of probe the entire space of the like the
yeah, we certainly cannot probe the whole space of models. Yeah. Right.
So Juan, maybe you are quite tired by now. 1 or 2 more questions, or
sure, yeah.
Yeah. So one general question regarding the original ADS-CFT model, like on the SUN theory you have. So that you showed had a lot of conservations, right? So
yeah, that's symmetry.
I think that when you generally when a system has lots of conservation, even its thermal states, like high temperature states, are not fully ergodic, so would not have this T log T kind of scrambling, right? So is that?
Yes. Well, no, we think that the theory is that yeah. So there was this original model which involved ADS 5 times S5 and n equal to 4 super young males, a particular sort of gauge theory.
Right.
And it's true it has many symmetries, and it's even integrable if you consider only the planar diagrams. But we think that black holes in those theories are still chaotic. And yeah, and we can actually calculate that there is a notion of quantum chaos that is very nice, which involves the out of time order commutators. And you can compute those in gravity, and for any black hole, it always gives you some maximal chaos, so very chaotic. And so we think that because of the behavior of simply because there are black holes in this theory, if the duality is correct, then the Yang-Mills theory should be chaotic. And we do expect it to be chaotic for very high energy states.
So just to understand a little bit, so the role which is played by this random random couplings in the SYK version.
Yeah, I would say that role is purely technical. So just to do the calculation.
I see.
So there is, for example, the example we were discussing about ADS5, that has very specific couplings. Okay. I also mentioned another example which is somewhat related to that, this quantum mechanical example. Yeah, I should probably have given a reference to this quantum mechanical example. It's called the Banks, Fischler, Susskind, and Schenker model. This model is just the dimensional reduction of n equal to 4 super Yang-Mills to 0 + 1 dimensions. And so it's a very explicit theory with very definite Hamiltonian, no random couplings whatsoever.
Right.
Yeah.
And the SYK, of course, has another feature, which is this long range feature. So is that coming here because you are kind of eliminating the gauge fields or something like that?
Yeah. Well, this comes here because these harmonic oscillators and fermions we're discussing, they interact all with all. And more specifically, you can think of them as arranged into n by n matrices. And there are terms that involve products of these matrices, and the matrices in this are all summed over. So all the various components of the matrix interact with each other.
Thank you. Maybe one question I was interested in, which is more directly to our interest, that of course when two black holes are interacting, kind of some degrees of those degrees of freedom on the neck are interacting, then a wormhole is forming. That picture, I mean, how specific to black holes does that picture need to be, like this large number of states, microscopic? So is it can you, when normal masses interact, can you think of some, I mean, and then they're going to, say normally two fields nearby are interacting. Is there a geometric, would there be a geometric?
No, I don't see. Yeah, I think this picture was specific to black holes. You need something very close to black holes to get this to develop.
I see.
Yeah, I don't think that, for normal interactions.
Right.
We can describe it within the effective field theory.
Right. And so when a mass is falling towards the black hole, that in the boundary description, if I understand, it's the spreading of the correlators, right?
That's right. So when the particle is falling, it's getting thermalized and with the rest of the
right. So when say a mass is evolving in free space, so it will also spread in the the radial, the theta and phi azimuthal direction as well, right? Just due to wave packet spreading. So is that is what, is there a counterpart of that in the boundary theory also?
So if you had a theory which contains both the radial and, both the radial direction and some angular directions, so there will be the operator would spread both in the somehow radial direction, which is just how many components it has, but also in the angular direction.
Right. Okay. So one is like number of entangled things, and the other is just the spreading of individual things. Is that?
Yeah. So I think we probably have to formulate the question a little more clearly. I think the point is that in these models that have angular directions, so the elementary fields typically carry the qubits at the boundary. They typically carry only, let's say, 1 unit of angular momentum, or a small number of units. If you have a particle that is localized on the sphere, means that it has many excitations with the same charge, the same elementary unit.
Right.
And then as time evolved, so in order for it to be localized, it needs to be a superposition of several high angular momenta, right?
Mm-hmm.
And then as first angular momentum is conserved, but it could be that that becomes less localized. Or
Okay, thank you. And spin is also emergent from the boundary, the spin of the particle. I mean, the intrinsic spin of the particle of a field. Is that, say, in the bulk? Say you have a spin half particle in the bulk. Does that?
Yes. Well, I think this question is more clear in higher dimensions.
Okay.
Yeah, so yeah, in higher dimensions, typically the spin of the particle is related to the spin of the operator that created it on the boundary.
Okay.
So, but that's because we have a global, somehow some symmetry, which is the rotation symmetry. And it's both a property of the boundary and the bulk theory. And so if you have a spin and a half, then you will, it will be a spin and a half part operator, will be fermionic operator on the boundary that creates something in the bulk.
Okay. Thank you so much. Yeah, we have kept you very long. Thanks for your time. So anyone else has any questions?
Maybe to answer better the question of the spin, I guess if you have theories which have many extra dimensions, extra internal dimensions, some of the spin degrees of freedom in internal dimensions also could be emergent. So.
Okay. Thank you.
Okay, thank you very much. Bye-bye.
Yeah, so, bye.